So the next thing that we want to do with this idea, now that we know what an average rate of change looks like, how do we interpret it in a scientific context, how do we compute it as a slope, a rise over a run, what we'd like to do now is something a little bit new. And to compute the average rate of change, not just between a couple of points that we select, but we select a bunch of different points throughout a relationship, like this graph here, and compute the average rates of change and keep track of how the average rates of change. In other words, if I'm a passenger on this plane, to keep track of when is my plane going up and when is my plane going down, and how quickly. So what we might like to do is to measure these average rates of change, and here in my Excel spreadsheet I've labeled them as dy divided by dx, only because I'm kind of lazy. On our sheets and usually in the context of mathematics and the sciences, those d's are replaced by capital letter delta. This capital letter delta, when you read it in English, means the change in. So how can we measure these average rates of change repeatedly and keep track of them for different values of x? In other words, for different places along this graph. So there are actually several different ways to do that. Again, because if we start with a set of data, and basically a set of data is what I've sort of graphed for you here, and it's usually where most scientific enterprise gets started in the laboratory, right? We go and we collect some data. From that data, we can find average rates of change between any 2 points in this data table that we choose. So we have, though, if we want to keep track of those rates of change, we have to decide, for example, if I compute the average rate of change between these 2 points, between x equals -2 and x equals -1. First of all, let's compute that average rate of change. So I'm going to place my left point here at -2 and my right point here at -1. And the average rate of change between those 2 points, according to the rise over the run, the rise here is 5 and the run is 1. So the average rate of change is 5 in this particular example between these 2 points. But then the question is, okay, great, it's 5. But which x value do we want that 5 to belong to? In other words, between these 2 moments in time, between maybe -2 seconds and -1 seconds, my plane has gone up at a rate of 5,000 feet per minute. But do I want to say that I experienced that increase at time -2? In other words, do I want to put that 5 here in my data table? Or do I want to put that 5 at time -1, right here in the data table? I have an option, and each of those options is going to give me a different method of computing an average rate of change. The former is called the forward differencing method. So in a forward differencing method, we compute an average rate of change, and we give that rate of change to the left-hand endpoint of our interval. So if you're using a forward differencing, you're planting your feet at the endpoint on the left, and you're looking forward to the next point. That's why they call it a forward difference. So we would record the 5 in the first column here. Whereas, conversely, if we decide instead to assign this rate of change to the right-hand endpoint of the interval, then we call that a backward differencing method, as though we're standing right here at x equals -1 and we're looking backwards in the data to the previous data point. Again, in each case, the rate of change is the same. The only difference is where we place that rate of change inside the table. So suppose I wanted to use a forward differencing to find the average rate of change for our next data point in the table, this x equals -1. What 2 data points would I use if I were doing a forward differencing at x equals -1? What rate of change would I need to find for a forward difference here? I would use -1 and 0. In other words, on my graph, I would choose this point here at x equals -1, and also this point here at x equals 0. And I would record the slope of this line, the average rate of change, at the point x equals -1. And so according to this line segment now, the average rate of change at that point is 11, between -1 and 0. 11. That same 11 would also be the backward difference rate of change at the right-hand endpoint of this interval at x equals 0. So same numbers, just placed at different places. Okay, so we've filled in the rest of the average rates of change, the rest of the slopes on this table. Notice, though, that there are a couple of boxes that must be blank. Namely, the box at the beginning of the backward differencing and the box at the end of the forward differencing. Because if I try to do a forward difference quotient, a forward average rate of change at this point, I would have to go to the right and find a data point here to do it with, but we don't have a data point there. We fall off the end of the data table. Likewise, for the very first backward difference at x equals -2, we would have to find a data point to its left to find that backwards rate of change, but we don't have one, so we can't do it. So we have to leave those two blank. But this also, choosing either forward or backward differencing, introduces a little bit of a bias into our average rates of change. If I'm always looking forward, if I'm always using the average rate of change to label the left-hand endpoint, that's going to kind of skew our average rates of change toward the endpoints that come first, to the left. Likewise with backwards, we would be biased toward the right-hand endpoints always. So the way to get one way of getting a more accurate measure of the average rate of change is to take the forward and the backward differences and just combine the two of them. Try to take the best of both worlds. In other words, let's just say we average them together. Take the forward difference and the backward difference, and we just split the difference, if you will. What we get is another differencing method called symmetric difference, which now is not biased toward the left-hand or the right-hand endpoint, but instead kind of takes the best of both worlds. And when we do that, though, we're going to not have a data point in the first column, and we're also not going to have a data point in the last column, because we don't want to average non-existent numbers. But for all these other numbers in the middle, we can average them. What's the average between 11 and 5? 11 plus 5 over 2. That's 8. The average between 11 and 11, that one's easy. Then I have the average between 5 and 11 again. The average between 5 and -7. And the average between -25 and -7, -16. And the symmetric differencing method is more accurate. It's a more accurate measurement of the average rate of change than either the forward differencing or the backward differencing. In fact, from a numerical analysis point of view, it's what we call a second-order algorithm. In other words, its accuracy as our intervals get smaller and smaller, its accuracy gets better and better at a strictly higher order than the accuracy of either the forward or backward methods, which are first order instead of second order. So what I'll be asking you to do is to take data sets like the data set that we have here and compute symmetric differences for those data sets to get a sense of how the rate of change in the data changes. What are the different values the average rate of change takes on in this table? And just to give you one last little bit of context here, let's pick one of these numbers in the symmetric difference, -1. Where does that -1 come from? It would be our symmetric difference that we assign at the point x equals 2. Well, here's where that -1 ends up coming from. When you split the difference between the forward and the backward, what we end up doing is really taking both a forward step and a backward step at the same time. In other words, we would be taking a step backwards to this point at x equals 1, and also a step forward to this point at x equals 3, and connecting those points with a line segment. And the slope of that line segment is -1. So a symmetric difference gives you a measurement of how things are changing sort of on both sides of the point, both on the left-hand side and on the right-hand side, by splitting the difference between the forward and backward methods of determining an average rate of change.